Okay, everybody. Today, let's talk about this concept of specific heat. It really helps us in many instances. Okay, so this is officially defined. I took time to write it. Energy required to raise the temperature of a unit mass of a substance by 1 degree. So if we start talking about units, you will see what I mean. So this is in the SI, like kilojoules, because as you know, joule is kind of small. So that is the energy per unit mass. So unit mass in the SI is kilogram, right? And then 1 degree, the unit, thermodynamic unit is Kelvin, right? Thermodynamic scale. But remember, as I'm increasing 1 degree, I can also increase one Celsius, right? They are the same thing, so that's going to be fine, okay? Because I'm looking at the delta over here, okay? I can also make the same argument for the British gravitational. So this is going to be the BTU. As you know, all the tables that we have at the back of our book is listed as a function of BTU. So I'm going to be sticking to that. We have the pound mass, right? That is the unit mass of a substance in British gravitational times, again, 1 Rankine or 1 Fahrenheit, okay? So if I want to put some number to it as an example for air, air at 27 degrees C, which is the room conditions, right? I need 1.005, almost 1 kilojoules of energy per kilogram, right? Per kilogram of air per Kelvin. So this is the actually particular number. However, this is not sufficient. Actually, this is the energy that I need to supply if the process is constant pressure. Basically, while keeping P constant, okay? I can also write the exact same thing. You can convert this, obviously you don't need me, but 0.24 BTU for pound mass times Rankine, right? Again, this is given as 80 Fahrenheit, okay? So you can see these. Important thing is this keeping pressure constant, okay? So let me actually take this while I'm talking about keeping the pressure constant. Why don't I look at this specific heat? Actually, I will have two paths in the process that I take, where I take the temperature by 1 degree or increase. I can take a constant volume. Okay? I can have in a case where my volume is not changing, okay, but I'm allowing the pressure, can change. I'm not making any restriction on it, okay. And this actually will be called CV. This will be abbreviated as CV. This is the specific heat for a constant volume process. That's where the V comes from. Okay, so this is going to be del U, del T, and as you know from the state postulate, I need two properties just to define. So that's why I'm raising as an example. It doesn't have to be just uniquely T and P. It can be other properties like a specific volume 2 as an example. Okay. But one thing to note, this is V is constant, volume is constant, okay? So, all right, so now I want to actually make a 1 minute break from the thermodynamics and focus on mathematics. I want to highlight this because I'm going to use this. Do you remember the difference between these two, du dt versus del u del t? Yeah, I just want to highlight this. This means that this is only a function of temperature. This means that this is a function of t is time. As an example, I'm giving an example in here. This can be, in addition to time, it can be a function of, again, like pressure, temperature, many things. So basically this del sign highlights the fact that this u is a function of not only t, but other variables too. I'm only looking at how it changes over time for this particular case, okay? Okay, I think that's enough of mathematics from my side to your side, okay? Let's proceed with the other option, okay? The other option is constant pressure, okay? So it's like reverse, right? You see, I keep the volume, that can change, but I'm keeping the pressure constant. And this time it doesn't surprise you, but I'm going to call the CP. P stands for the pressure. But this, be careful, del H, enthalpy, del T. Okay, again, this can be a function of temperature and pressure as an example, but this time I'm keeping pressure constant. Okay, and I want to touch upon this constant volume, constant pressure. I want to actually go ahead and say about this. Do you remember that we have something called boundary work? right? I discussed in actually earlier in this module, one of the segments or multiple segments. And that one, what we said is this work is equal to PdV, right? Do you remember that? So if I do a process, if I go through a process with constant volume, what happens to the boundary work? It becomes zero, okay? So what it means is all of the energy that I add, like let's say this particular case, this is for constant pressure, but if I add this much energy into the system, all of them will go into the increasing temperature of what I have in there, okay? But if I heat in a constant pressure case, which is this case, what happens is, do you remember isobaric process? I get myself P times V2 minus V1. So there will be some work done. So which it means is not all 100% of the energy that I'm putting in to go to the internal energy increase of the fluid that I have, but also it will use it to work against the boundary, okay? So typically then, but well, not kind of always, then my Cp values will be more than Cv. So if I look at air, for instance, it says 1.005. I don't remember off the top of my head now, but it is lower value than this. It was 0.72 or something like that. I don't recall the exact number now. Okay, so that's the two ways that we can do this expansion in this particular case. And remember, I talked about table A1, I talked about table A4, A5, A6, A7, A8, and I didn't talk about A2 and 3, right? So this is where I come in. Now I'm going to talk about A2 in about, like, soon I'll talk about A3 too, okay? So this appendix 1, A2 and A2E in appendix 2 will give me an SI and BG, CP and CV values at the room temperature, but also it gives me at various temperatures, okay? And this, I wanna, I actually don't need to say this, but obviously the CV is not just one value, right? It's a function of like the pressure, the temperature in a general case, and we'll boil down that a little bit down, but in general cases you can see it's a function of the temperature, okay? So you cannot just say like CV of air is, I said at this particular temperature, right? You see? So be careful about that. Don't assume that it's going to stay constant, and this may incorporate significant error to your analysis, okay? Now what I want to do is, okay, now we know what a specific heat is, kind of, right? So why don't I take the specific heat, of ideal gas, okay? So I am not going to show it, but basically when the experiment's done, it shows that the CV does not depend on the pressure. What I'm saying is it's only for ideal gas. Careful. Students tend to exaggerate this. CV does not depend on T. So then CV is only a function of T. Okay? So P's out. So now you see the state postulate? So now I only need one of them, one property. Okay? Obviously CV is a property too, right? That's right, this is equal to CV, right? CV is equal to CVT. And again, why don't I go ahead and underline this like 3 times, just to, well, I can't even underline, just to highlight that this is really, really important. Make sure you know the title of this segment, okay? CVT is only for ideal gas. I see this often, okay? So CV will be del U, del T, you know this, at constant volume. So then this becomes du dt. You see, I explained this. So then the right hand side is only a function of temperature, and you see what I wrote over here? This is only a function of, in this case it was time, but now it's temperature, and it's the same variable. That's the important part. So I can write du dt, okay? And this gives me some flexibility in terms of how I want to write this. I can move this around, so my du becomes cv dt, right? Right from here, actually, this and this, right? Okay, and so wait a second. CV itself is a function of t and dt, so you can clearly see now that u is, as I mentioned, u is only a function of t, and it's worth writing over t here. U is also a function of t only, for ideal gas only. I don't want to keep repeating myself, but I feel like I do, okay? So if you take the integral of both sides, you can get u2 minus u1, you can get t1 to t2, cvt dt, okay? One thing I want to mention in here, actually I'm going to solve a question to illustrate this too. This point I'm making here is this. So if you read a table, right, I mentioned the table, right over here. If you're reading a table, well, which one are you going to read? Let's say that it goes from 300 Kelvin to 900 Kelvin. Are you going to read it 300 Kelvin this value or 900 Kelvin this value? Because these are just numbers, not a function. It's not given, okay? So what am I going to do? Well, I'll typically take the average temperature, okay? That's the best I can do. Again, I'll solve a question to illustrate my point, but just going to give you the heads up, okay? All right, so now why don't I look at this is all about the CV, but less about the CP for this, okay? So this is DH, del H, del T, at P constant, right? That was how we wrote it. Okay, so why don't I do this? Do you remember this? U plus PV, right? And do you also remember this is basically the relationship between enthalpy, specific enthalpy, and specific internal energy. And this is pressure, this is specific volume. And you kind of remember, or I really do hope you do remember, that for an ideal gas, PV is equal to RT. So I can simply write this to H is equal to U plus RT. Wait a second, I said that this is only a function of T. Right here, right? Right here. Well, this is only a function of temperature because R is a constant, T multiplied by R. So then H must be only a function of T2. Another point I want to make. H of T only, let's write only. Again, for ideal gas, I don't want to keep writing the same thing, okay? But if I go through the same process that I did up there, you're going to get that this dH will be Cp of T this time dt, okay? And if I take the integral as usual, I'm going to get myself H2 minus H1 will be equal to T1 to T2 Cp T dt for ideal gas only, okay? And I want to look at something else as well. At the beginning of the segment, what did I say? I said that Cp is always greater than Cv. So now for ideal gases, I am lucky in a sense that I can quantify how much in a minute, okay? And for that I need to do a little of a trick, which I actually started up there. H is equal to U plus RT, right? Or this also can be written U plus PV, right? I'm going to use RT for a reason in a minute, and I'm going to take the basically derivative or differentiate this particular equation. So I'll get dH will be equal to du plus, well, dRT, but I need to look at this a little bit. Du plus R is constant, right? R dt. Okay. So what I'm going to do is I'm going to divide both sides of the equation by d temperature, dt. Can I do that? Yeah, why not? As long as I'm doing it to the both sides, I should be good to go. dH dt will be equal to du dt plus R dt dt. Well, I'll do one side, which is easy. I'll ask the other to you. Okay, this is one. What about this? And what about this? Do you remember those two? Yes, I remember myself. So this is Cp, this is Cv. So what did I get? Cp is equal to Cv plus R. So this is the relationship, again, only for ideal gas between the Cp and Cv. Okay? And one more thing is I also have specific heat ratio. And this is abbreviated as K, lowercase k. And this K is defined by Cp by Cv. We use this not at this point. It's not like why is he doing this, but it will come in handy soon, okay? Trust me on that one. And monoatomic, you know what monoatomic, right? Single gases, again, monoatomic gases, K will be right around 1667, okay? If I have diatomic gases, and what is actually more interesting in this particular case is air included, this K is equal to 1.4, okay? So now I can get, if I know Cp, I can get Cv. Again, that's not the only reason why we did this K business, but it will make more sense soon, okay? Before I end this segment, I also want to talk about liquids and solids, okay? So remember what I did. At the first beginning of this particular segment, I started specific heat. I focused into the ideal gas, which is a gas. Now I'm saying that why don't I look at liquids and the solids? Okay. So one thing I want to do right off the bat is the solids are incompressible. So what I mean by this? What I mean by this is that if I push a solid, let's say that you have a steel block. If you apply pressure to it, it's not going to squeeze, right? It's going to stay exactly the same volume as that. Okay. So basically, this doesn't mean volume is constant. Okay. Incompressible and volume is constant is two different terminologies in fluid mechanics, but we'll pretend it is good enough for now. Okay. So basically, the specific volume or volume itself is constant. Okay. And I actually will make an assumption over here. This is kind of not bad of an assumption. I did a question about it. Let's do a PV diagram, and let's say this is my steam dome as an example, and the graph looks like this, right? And for a particular temperature, right? So what I am saying is, you see how steep this slope is, and I can kind of go ahead and say that, you know, like this specific volume right over here can be approximated as here. And I actually did a question. I illustrated there is like 2%, if I'm not mistaken, something like that, very small. Okay. So what we will do is we will make that assumption too. We will say that the volume is also constant for liquids too. So I'm gonna add plus liquids over here. Okay. Not a huge deal. I'm telling you, it's not a big deal. Okay. So what it means now is, as I have this, if you you know, from observations, we see that the Cp and Cv does not have a differentiation anymore. So I don't have to have like, because remember, P constant, V constant, so that doesn't really matter because V is constant, okay? So Cp will be equal to Cv, and we are going to call it, you know, C. And the same thing that we discussed up here, the C, or, you know, Cp or Cv or, you know, C, this will only be a pressure will not be there as it is incompressible. It's only a function of temperature. I never said anything about temperature. I want to highlight. So if I change the temperature to here, obviously this volume for these two cases for a closed system, which I'm covering now, will not be the same. Okay, there's a significant difference between this and this value, right? So I'm only saying that it is a function of temperature. It is not a function of pressure. Okay. Again, I said we discussed A1, we discussed A2 up there. Now I'm going to discuss A3. A3 and A3E, one is in Appendix 1, Appendix 2, SI, BG. This will give you the CV and CP information that you need for solids and liquids, okay? So go ahead and read that off, okay? But, you know, due to this, now I'm going to show something over here. When the CV was only a function of time, what did I get? Only a function of temperature. What did I get? Because I get this, right? So I have the same relationship over here too. So let me copy paste this. Give me 1 second, please. Okay, I'm back. Okay, now you can see U2 minus U1. Same thing can be said because you see it is only a function of temperature, just like that. Okay, and sometimes we call this to be C average. There's some kind of an error. I will solve a question to illustrate this. T2 minus T1. Okay. And let's look at this, you know, now I'm done with the U. Let's look at the H, okay? Do you remember I had this dH is equal to du plus dPV, okay? And can I write this PV is equal to RT? Yeah, you can, but you will be horribly wrong, okay? Because that is only for ideal gases. This is liquids and solids. You cannot do it. It is PV. This is the original definition. You cannot say RT, okay? So this will be du plus VdP PdV. Okay. Hey, up there I said dV is 0, right? V is constant. As V is constant, so this is gone. Okay. So now I have two paths for me. You can see over here, dH will be equal to du plus dP. So this may be what you have. Okay. You may need to analyze this. But for solids and isobaric process involving liquids, right? Look what happens to this dP. Solids, well, like I said, you have a steel block. You apply some pressure to it. Do you think it's going to change the shape? Nope, not really. Okay. So it's going to stay exactly where it's at. So then dp will be 0, so that you're going to get dh is equal to du. Okay, so in this particular case, you're going to get h2 minus h1 is equal to u2 minus u1 will be equal to C average. I don't have to differentiate anymore, T2 minus T1. So I simply copy pasted this, you see this? I copy pasted this over here. Okay, but I can also have a liquid that goes through isothermal, which is the temperature constant process. I can, absolutely I can, why not, right? Looking over here, U2 minus U1 will be C average times T2 minus T1. What is T2 minus T1 for an isothermal process? 0. So then, okay, then dH will be, du will be 0. This. And I can write this H2 minus H1 will be equal to this, P2 minus P1. Okay? So this is gonna do it for the concept wise. I will solve a couple questions and I'll be right back. Have a good day. Take care.